Hey guys, Angel here, and I'm actually pretty excited to go through this problem with you because when I first approached the elevator problems, I really had no idea what was going on. The change in the person's weight just didn't really make sense to me, but now, a couple of years after physics, it definitely makes a lot more sense. That's probably not what you want to hear, but hopefully, I can just share my understanding and maybe help you out a little bit. But let's go ahead and take a look at the scenario. A gentleman of 550 newtons is riding an elevator while standing on a scale. What does the scale read when the elevator is moving up at 5 meters per second? Let's go ahead and draw a free body diagram of this gentleman here. We've got the force of gravity down, and it gives us the weight is 550 newtons. And then we've got the normal force, or the force of the scale on the man upward, and that is that's what we're going to try to figure out here. So what does the scale read when the elevator is moving at 5 meters per second? So if it's moving up at 5 meters per second, that means that it is not accelerating. We're given a velocity. So that means that we don't have a net force. So our net force is equal to 0 because our acceleration is equal to 0, right? So here's our equation. And when our acceleration is equal to 0, our net force is equal to 0. But we can still use this information to solve for the components of the net force. And the components of the net force in this case are the normal force and the force of gravity. And so the normal force with the force of gravity, the sum of those two shall equal 0 newtons. We're given the force of gravity, which is negative 550 newtons. And so it goes without saying that the normal force in this case is 550 newtons in the positive direction, and that's what gives us a net force of 0 and allows us to move at a constant velocity, because if we did indeed have a net force, we would have to have an acceleration as well. So what does the scale read when the elevator is moving up at 5 meters per second? It reads 550 newtons, or if it's in kilograms, 55 kilograms. And we got that by dividing by the force of gravity to turn newtons into kilograms. I'm sorry, the acceleration of gravity. And so the next question asks very similarly, what does the scale read when the elevator is moving down at 4 meters per second? So don't be tricked by the change in direction. Both, either moving up or moving down, they're both moving at a constant velocity, which again means that our net force is equal to 0. The components are still the same, and the gravity didn't change, and so that means that our normal force is also equal to 550 newtons, so the scale reads 550 newtons, or 55 kilograms. So now let's take a look at the third scenario, and this is where it starts getting a little trickier. If the elevator goes from rest to 4 meters per second in the upward direction in 0.5 seconds, what does the scale read while it is increasing in speed? So while it is accelerating, in other words. So first thing we're going to have to do is find the acceleration with the given information. And we can use our velocity equals acceleration times time equation to solve for the acceleration. We reached 4 meters per second in a matter of 0.5 seconds. And when we solve for the acceleration, we get that an acceleration of 8 meters per second squared. So we've got our acceleration, and then we've got the mass of the man. Even though it's given in newtons, we can turn that into kilograms, and that would be 55 kilograms. So the net force is equal to 55 kilograms times 8 meters per second squared. And so our net force is equal to 440 newtons. And then the components of the net force we already discussed are the normal force and the force of gravity. And those together will equal our 440 newtons. And we know the force of gravity. We're given that. That is negative 550 newtons. And now what we'll need to do is solve for the normal force, which is what is measured on the scale. The normal force is the surface underneath the man. It's this little black thing right here, and that's pushing up on the man, and the man's pushing down on the scale, and that is what is telling us how much he technically weighs during that acceleration. So when when we solve for the normal force, we get that the normal force is equal to 990 newtons. That is much larger than the 550 newtons that the man weighs. So now we have to ask ourselves, does this make sense? And I'm going to hope to make sense of it for you now. This scale is on the elevator. It moves with the elevator in this scenario. And so when the elevator begins to accelerate in the upward direction, the elevator and the scale accelerate first before the man do. They have to push up on the man in order to also get him accelerating. And in that very small amount of time that the elevator accelerates, it's going to push on this man with a little extra force because it wants to get him moving. He's stationary, right? So when we're on an elevator, we're stationary. We're not moving in any direction. But when the elevator begins to accelerate, it has to push us in order to get us to accelerate as well. And in this case, moving in the upward direction, it's going to push on us. And it's the same concept as pushing down on a scale and causing it to increase in value. If you have a scale at home, you can sit on the scale, but then if you push on it with your foot even more, it's going to cause that force to increase. It's going to cause that measurement to increase. And the same concept goes here. So when the elevator accelerates upward, we can expect a increase in the measurement of the scale. So the answer here was 990 newtons or 99 kilograms. It doesn't tell us whether it wants to answer newtons or kilograms, so we'll just add both. So just again, if the elevator is accelerating in the upward direction, so upward acceleration, it equals an increase in the measurement of the scale, and that is because the scale is pushing on the man, and the man at the same time is pushing down on the scale and causing that scale to increase in value. Now let's take a look at the last scenario, and that is if the elevator goes from rest to 4 meters per second in the downward direction in 0.5 seconds, what does the scale read while it is increasing in speed? So it's increasing in speed, but because it's in a downward direction, we're technically gaining a negative velocity, and so we have a negative acceleration. And the scenario is the same, so now we have a negative 8 meters per second squared. And those negative 8 meters per second squared, we would multiply that by the mass of the man, which was 55 kilograms, to get the overall net force. And we're going to have the same 440 newtons, but this time it's going to be negative because of the negative acceleration. So negative 440 newtons. We're going to see how that plays out in in our normal force of the measurement of the scale. And so again, we're going to go ahead and put the components of gravity as the normal force minus the 550 newtons of the gravity on the man. And then when we solve for the normal force, we get that the normal force is equal to 110 newtons. And then if we convert that to kilograms, would be 11 kilograms on the scale. But the normal force is 110 newtons. The scale might read in newtons or it might read in kilograms, but the normal force is 110 newtons. So what does this mean? This means that the scale is reading less than what the man truly weighs. How does this make sense? And again, I'm going to try to make sense of that in the same scenario. So when the elevator was moving up, it had to push on the man to get him to move up as well. But this time, when the elevator moves down, it leaves the feet of the man for just a split second. So the man is literally floating in the air for just a small amount of second. Not all the way in the air. I shouldn't say that because there is still a measurement on the scale. In this case, we've got 110 newtons. So he's still on the scale, but he has lifted off just enough to make the scale believe that he's going to come off of it. Because when the elevator moves down first, and then the man has to fall with gravity to catch up to the moving elevator. And so for just a small amount of time, the elevator is going to leave that man's foot, and the man is going to have to fall with gravity in order to catch back up. But in that time, that split second, the force or the measurement on the scale is going to be reduced because the man has now technically put less force on it because the elevator is leaving him. And so let's just recap real quick. If the elevator is moving at a constant velocity, then we have the force of gravity is equal to the normal force. When the elevator is accelerating in the upward direction, then we have the normal force is greater than the force of gravity. And lastly, if it is accelerating in the downward direction, then the normal force is less than the force of gravity. And that's because of the split amount of time that the scale is interacting, is either pushing on the man or literally leaving the man's foot. And so hopefully that makes a little more sense to you as far as the concepts of elevator questions. I know that for me it was very tough, and I hope that makes a little more sense to you. If you have any questions, please leave them in the comment section below. If you would like to stay updated with the videos, go ahead and subscribe. And thank you very much for watching.